The biggest difference between finding area and finding volume is that in area, we're working with a two-dimensional object. We're working with a shape that has two ways of measuring it, length and width, or length and height. It's flat. This is even true when we are finding surface area. Even though surface area deals with three-dimensional objects, when we're finding the surface area, we're unfolding those objects and making them flat. We're finding the area of each separate side, which is flat, and then putting that all together. When we're dealing with volume, we're talking about three-dimensional objects, and we're talking about filling that space. With area, we're covering the space of a two-dimensional shape. With volume, we're filling the space in a three-dimensional shape. Getting back to the basics and making sure that students can clearly explain that difference is very important. To find the volume of a cube, what we're doing is taking a unit like the one that you see here, which is a smaller cube, and we're trying to figure out how many of these it would take if we put them inside this bigger cube and filled it up. Just like we did with area, we can do this by thinking about a row at a time. So if we think about making a row of these cubes across the bottom, let's just say that it would take 4 cubes across and 4 cubes this way, because the sides are all the same, to make a row that would fill the bottom. So if we did that, we would have 4 cubes here, and we would have 4 cubes going back. So we have 4 in a row, and we have 4 rows, and that will cover the bottom of this cube. In some ways, that's like finding the area of the bottom. If we picked this cube up and looked at the bottom and looked at just that flat part as we looked up at the bottom, that's what we would see. So we know that we have 16 cubes to completely fill one row of this cube, this larger cube. Now we need to figure out how many of those rows can we get in here. So if we make another row, and we make another row, and we make another row, we will find out that we can do that 4 times. We can have 4 layers in the height. So if we have 16 cubes at the bottom, making the bottom row, and we know we have 4 rows going up, we can take 16 cubes times those 4 rows, or we can add 16 4 times, and we get 64 cubes. It will take us 64 cubes to fill this larger cube. So what have we just done? To find the row at the bottom, we actually took 4 times 4. We took one side times itself to get the row at the bottom, and then we took that times how many rows we could make, which was again times 4. So we're taking the side times the side times the side. That means we're taking the side cubed to find the volume, because the sides are all the same. We're making a larger cube out of the side, and we're filling that cube with these smaller cubes. So what would our label be? We have 64 what? We have 64 inches cubed, if they're inches. Why are they inches cubed? Why are they cubic inches? Because they look like a cube and they are an inch on every side. We want students to understand that logically so that they can see what a cubic inch actually looks like, so that they can see that they're taking that cubic inch and filling this larger cube with them, and that what they're doing is making a layer at the bottom and making a bunch of those layers going up until the cube is filled, and the formula that helps us do that is side cubed equals volume, length times width times height. We can use exactly the same idea to find the volume of a rectangular prism, except this time we don't have sides that are all the same. So as we're looking at the shape, the first thing we need to figure out is how many of those cubes would it take to fill the bottom row of this shape. So we would have to go across and fill with our cubes. So let's just say that it took 8 to go across. So there are 8 cubes going across, and let's just say that we have 4 of those going back. So we have 8 across, that's our length. we have 4 going back. That's our width. So if we take the length times the width, that will tell us how many cubes it takes for that bottom row, just like we did with the cube. Now we need to know how many of those cubes will it take to fill this. How many layers will we have? So we might say 1, 2, 3, 4, 5. It's going to take 5 of those rows to fill this container with cubes, so it's full to the top. So if we have 8 here and 4 here and 5 rows, that's our height. So now we need to take that length and width, which gave us the number of cubes in the bottom row, times the height, which will tell us how many of those rows we have to have. So the formula for finding the volume of a rectangular prism then is length times width to get how many cubes are in the bottom, times height to figure out how many of those rows there are. And that will give us the volume of the rectangular prism. When we have a label, what is our label going to be? We filled this box with these cubic inches again. So our label would be inches cubed because they look like a cube and they're an inch on every side. We have 3 dimensions. We're filling a 3-dimensional object with 3-dimensional units, which is why they are called inches cubed. We're going to use the same logic to find the volume of a pyramid. When we do this, some of the things are the same and some of the things are different. What's the same is we still want to know how many cubes would it take to make a row at the bottom of that figure. We want to know how many of these cubic units could we fit inside that pyramid to make a row at the bottom. We also want to know how tall the pyramid is. We want to know the height. However, as you can see here, as we make these rows going up, they're going to get smaller and smaller and smaller. So we can't just take length times width to get how many cubes are in the bottom row, and then take it times the height to figure out how many of those rows we need, just like we did with the rectangular prism, because the rows are getting smaller. So we have to do something to this. We still want to take length times width times height as we did before. What that's going to give us is the volume of the rectangular prism that we could build around this pyramid. If we took length times width to get how many cubes are in the bottom, times height to figure out how many rows there are, that would give us the volume of this entire prism. What we do know, however, is that the empty spaces here that we have not filled would take up 2 of these pyramids. We could actually fit 3 pyramids this size in the related rectangular prism. Now, how do we know that? There are all kinds of mathematical proofs that could help us figure that out. But for elementary students, I think it's better just to show them that it works. This is a law of mathematics in nature that works. We could show this to elementary students if we had hollow figures. For example, if we had a hollow pyramid that we could turn upside down and we could actually fill it with water, then students would be able to see that if we took the water from that pyramid and if we put it in the related rectangular prism, the water would go in 3 times. We could fill it once, we could fill it again, we could fill it again, and it would take 3 of those to fill this prism. So that would show them that we can fit 3 pyramids inside the prism. That would mean that the volume of the pyramid is 1/3 of the volume of the rectangular prism. So what does that mean for our formula? It means that we are going to take length times width times height, just as we did to find the volume of a rectangular prism, but we're going to divide that by 3 because we can fit 3 pyramids inside that prism. We're using something that we already know to do something new. We're using the relationship between two objects to apply old knowledge to a new situation. It's mathematical law. It's how things are in nature. Students may forget this formula. They may memorize this and they may forget it. But if they understand that the space a pyramid takes up is 1/3 of the space of its relative prism, they will be able to go back and figure out the meaning of the math. To find the volume of a rectangular prism, we took length times width to find the first row, the bottom row, how many cubes it would take to fill the bottom row, and then we took that times height to figure out how many of those rows we would need. Finding the volume of a cylinder is very much the same. The only thing that can be confusing to students is that the cylinder is round and they can't picture filling it with cubes. So if we relate this formula to the formula for finding the volume of a rectangular prism, it will help them. Again, we're building new knowledge on an old understanding. So with that rectangular prism, the first thing we did was to find the area of the bottom. We can do that also with this cylinder. What is the area of the bottom? And then we can take that area times the height to help them see how many of those layers it would take to completely fill the cylinder. How do we find the area of a circle? Hopefully we've already taught that and we've taught that well. The area of a circle is pi times r squared. That will give us the area here. Now we need to know how many of those layers will it take? That's the height. So if we take the height times pi r squared, we will have the volume of this cylinder. A nice way to show this to students is to use something like a tennis ball container, and we can actually have them feel the bottom and say, okay, here's the area of the bottom, now we're going to fill it up. How many of those layers will we need to get to the top? Again, this is an excellent example of how math builds knowledge as we go. We need to make sure we teach those basic ideas very well so students can use them in new situations. In this case, they're using the knowledge they learned about finding the volume of a rectangular prism to finding the volume of a cylinder. It's very similar. And if they can see that, and if they've worked with real objects, they might be able to apply that old knowledge in these new situations much more easily. Applying old knowledge in a new situation is exactly what we have to do when we teach students how to find the volume of a cone. We've already taught them how to find the volume of a cylinder, and we've already taught them that the volume of a pyramid takes up 1/3 of the space of the volume of its related rectangular prism. When we teach students how to find the volume of a cone, we're using both of those pieces of information to help them. So what we're thinking here is, if we find the volume of a cone, we need to find the area of the bottom and take it times the height. That's what we did when we found the volume of a cylinder. We know, however, that if we find the volume of a cylinder, what we're really finding is this. We're finding the volume of this entire shape. And that's not really what we want. What we want is the volume of just the cone that's inside that cylinder. But we know that when we found the volume of a pyramid, it took up 1/3 of the amount of space of its related rectangular prism. That's also true here. We could fit 2 extra cones in this empty space. If we filled this whole space here empty to fill up the cylinder, we would be able to fit 2 more of these cones. That means that 3 of the cones would fit in this cylinder. So what we need to do is find the volume of the cylinder and divide it by 3. And that will give us the volume of just this cone. So how did we find the volume of a cylinder? We found the area of the bottom, which is the area of a circle, pi r squared, and we took it times the height. That gave us the volume of the entire cylinder. Now we need to divide it by 3 because 3 of these cones will fit in the space that the cylinder has. So that will give us the volume of a cone. We're also going to use information we already know and apply it in a new situation when we talk about the volume of a sphere. And we can do this in a couple of different ways because the volume of a sphere has relationships with a couple of different shapes. To begin with, we're going to do something similar to what we did when we talked about the area of a circle when it's compared to the square that we could create outside the circle. So if we take this sphere and we put it inside this cube, so it completely fills it up. It's kind of hard to do that and make it look realistic. But let's just say that the sphere is filling up the cube as much as it possibly can. We can then compare the volume of the sphere to the volume of the cube. Now we already know how to find the volume of a cube. We know that we can do that by taking the side, whatever the side is, and we can cube that side because it's the length times the width times the height. And that will give us the volume of the entire cube. But the sphere doesn't take up the volume of the entire cube. If you'll notice, of course, there are corners that would need to be removed, and there would be extra space in the sphere around those corners that would also need to be removed. So if we could do that, if we could remove the corners in that extra space, then we would know the volume of a sphere. The formula for finding the volume of a sphere is an interesting one. The formula is 4/3 pi times the radius cubed. So let's take a look at that and see if we can figure out what that relationship would mean. Here is a radius, here is another radius, here is another radius. So if we use those 3 to create a smaller cube inside this cube, we now have 1 radius cubed. This is a cube made out of the radius. How many of those would we be able to fit into that larger cube? Well, if we think about it, there'd be another radius going this way, so we'd have another one here. We'd have another one behind, we can't really see it, and we'd have another one back here. So we would have 1, 2, 3, 4 of those on the top layer. We would have another 4 of those on the bottom layer. And again, my drawing isn't exact here, but we would have 1 here, 1 behind, 1 here, and 1 around behind where we can't see it. So there would be 8 total of these small cubes inside the larger cube. So we could take the radius cubed, whatever that is, times 8 to get the volume of the entire cube. But as we look at the sphere over here, we aren't filling the entire cube. We need to get rid of those corners. So we need to think about how is the formula doing that for us? How is that formula figuring it out for us? Well, we know that the radius cubed is one of these. And if we took that radius cubed, whatever that amount is, times 8, we would have the entire cube. So how does 4/3 pi compare to taking it times 8? Taking it times 8 gives us the entire cubed. What about the 4/3 pi? Let's think about that. So pi is about 3.14. If we take that times 4/3, we end up with a number around 4 19/100ths, 4.19. Interesting to think about the fact that that is about half of the 8, if we look at it that way. So in one case, we'd be taking r cubed times 8 to get the entire cube, and we'd be taking r cubed times 4.19 to get the volume of the sphere. Does that seem sensible? It's interesting that most people, adults and students, if they're asked to predict, would say that the volume of a sphere, when put inside the cube, takes up more than half the space. But mathematically, the truth is, it does not. It actually takes up slightly less than half the space. If we eliminate all these corners and all that extra space in there that we talked about, we end up with slightly less than half of the space of the cube. With students, we can show them that by having hollow figures, as we discussed before when we were talking about a cone and a cylinder. If we had a hollow sphere And if we had a hollow cube, we would indeed find that the volume of the sphere is about half of the volume of the cube. If we filled a hollow sphere with something and then put that in the cube and did it again twice, it would just about fill up the cube. That's mathematical law. That's just the way the relationships work. And that's what pi is doing for us. It again is the magic number. Taking 4/3 pi times the radius cubed cuts off the corners and eliminates the extra space that the sphere leaves when we have it inside its relative cube. Another interesting relationship just to think about is this. If we put the sphere inside a cylinder that was the same size or close to the same size, we also find something very interesting. We find that the sphere takes up 2/3 of the space of the cylinder. And what else is interesting is that a cone takes up 1/3 the size of a cylinder. So in a cylinder, you could fit one sphere, 2/3 of the space, and one cone, 1/3 of the space, which means that the sphere is actually twice the volume of its relative cone. All of these relationships are fascinating, and we want students to work with real objects and work with drawings until they can see those relationships. Students may forget this formula. If you ask them, what is the formula for finding the volume of a sphere, they may not be able to tell you 4/3 pi times the radius cubed. They may forget that. But they probably will remember, if they've worked with real objects and drawings, that the volume of a sphere is about half of the volume of the cube, or the volume of a sphere is 2/3 of the volume of the cylinder. Those relationships are so important. They will be able to understand mathematically what's happening by seeing it. They will be able to relate one shape to another. They will understand that these are mathematical laws in the world, and they can at least estimate answers and know the relationships. And that's what this is all about. It's all about understanding what volume is. It's all about understanding how the volume of one shape compares to the volume of another. That's the meaning of math.